welcome. You're here because you want to get smart about what's shaping the future, quickly, but, properly. So let's dive right in. Today's topic, Rotating Detonation Rocket Engines, or RDREs. We've looked at some really compelling material suggesting this isn't just another tweak, it could genuinely reshape aerospace. Our goal today, to really get our heads around why these RDREs are causing such a stir, why they're seen as this potential game changer for, well, both defense and commercial flight.
Yeah, and what jumps out right away is just how different it is from traditional rockets. I mean, for decades, it's all been about deflagration. It's basically a fast burn, sure, but it's subsonic. Think of the flame coming out of a standard rocket engine. That's deflagration.
Okay, let's unpack this then. So a normal rocket is like a powerful controlled fire. What's the fundamental difference with an RDRE? What makes it, revolutionary?
The key word is detonation. Instead of that subsonic burn, RDREs create these continuous supersonic shock waves. Picture really, really fast explosions, tiny ones, chasing each other around a ring-shaped chamber, an annular chamber. It's not just burning faster. It's a completely different physical process for releasing energy. It compresses the fuel and oxidizer and reacts them at, well, hypersonic speeds within the wave. This generates a much more powerful, more efficient exhaust. It's maybe like the difference between a torch and a series of focused, controlled blasts.
Huh. So it's not a steady push, but this incredibly rapid cycle of tiny supersonic bangs creating thrust sounds way more energetic. But okay, how does that actually help? What are the real advantages for, say, a rocket or an aircraft?
Right. That energetic process gives us some pretty major benefits. First up, a big jump in fuel efficiency. Because detonation gets more energy out of the same amount of propellant compared to just burning it, you need less fuel for the same thrust. And we're not talking small percentages here. This could really change the economics of getting to space or flying long distances. Second, you get a much better thrust-to-weight ratio.
Meaning more power for less engine weight.
Exactly. Significantly more power for the engine's size and mass. So you can imagine designing planes or spacecraft with engines that are much smaller, much lighter, but just as powerful, or even more so. That opens up design possibilities.
Smaller, lighter, less fuel. That's definitely a compelling mix. Are there other advantages?
Well, somewhat surprisingly, the design can actually be simpler in some ways than traditional engines, often fewer moving parts. And that simplicity, points towards potentially less maintenance, better reliability, critical stuff in aerospace, and also a better thermal efficiency. It sounds weird, but some RDRE designs might actually run at lower overall combustion temperatures, even with the intense detonations, which could mean less heat stress on parts.
Okay, here's where it gets really interesting, at least for me. The reports we saw really stress how RDREs could be key to closing the hypersonic gap. Can you explain that? Why is this tech so crucial there?
Definitely. So the perception right now is that the U.S. might be a bit behind countries like Russia and China when it comes to having working hypersonic missiles, things that can fly and maneuver consistently above Mach 5. The kind of power density and efficiency RDREs offer. That's seen as, well, pretty essential for the U.S. to not just catch up, but maybe even leap ahead. You need incredibly powerful and efficient engines to sustain those kinds of speeds, and RDREs seem to fit the bill.
So it's not just reaching Mach 5, it's staying there, maneuvering effectively, which makes them harder to shoot down.
Precisely. RDREs could enable much faster strike capabilities, just less time to target. And if the missiles are smaller and lighter because the engines are, they could potentially maneuver more sharply, makes them way harder to intercept, better survivability. And the fact that NASA and the DoD are having successful tests, both on the ground and in flight, well, that shows it's moving beyond just theory. It's becoming real.
Right. And the reports also got into specific military uses. What kind of things are we talking about?
Oh, quite a range. Hypersonic cruise missiles are a big one, speed and range advantages there. Also, boost glide systems, where something is launched high and then glides back hypersonically. RDREs could be part of the initial boost phase or potentially even air-breathing hypersonic vehicles. There's talk of using them for more efficient spaceplane launch systems too, making orbit access easier, and maybe even upgrading propulsion on existing tactical aircraft down the line.
That's a pretty major potential shift for military aerospace. Yeah. But it's not all defense, is it? The commercial side sounds just as transformative. What could this mean for how we travel?
Yeah, this is where it gets really exciting for, well, everyone eventually, maybe. Think about RDREs in spaceplanes for intercontinental travel. The reports mentioned New York to Tokyo in under 2 hours.
Wow, under 2 hours.
Yeah, and also this idea of suborbital point-to-point travel, basically hopping up to the edge of space to cut down travel times between, say, London and Sydney dramatically. And beyond just the speed, that higher fuel efficiency could mean lower fuel costs, potentially fewer emissions per passenger over those huge distances.
Yeah.
Big implications for, global business, tourism.
That NY Tokyo time is just hard to wrap your head around. And it looks like the private space companies are already jumping on this.
Oh, absolutely. Some of the big names are already investing. Companies like Relativity Space, Blue Origin, Rocket Lab, they're looking at RDREs. They seem particularly interested in how compact RDREs could make rocket engines more efficient, maybe more reusable for launching satellites or even for deep space stuff. And, if the tech proves itself, you can bet commercial airlines, cargo companies, they'll be looking very closely, too, for that speed advantage.
Okay, it sounds amazing, but the reports were also pretty clear that this isn't easy. There are some major technical challenges, right? What are the big hurdles?
Yeah, definitely not straightforward. Number one is probably just keeping the detonations stable and consistent. Controlling those continuous supersonic shock waves reliably, especially in a full-scale engine, well, it's tricky. Very complex physics involved. Then there's the heat. Intense heat from these detonations. You need completely new thermal management systems, materials, and cooling techniques that can handle extreme conditions.
And the materials themselves must take a beating.
Exactly. Material fatigue is a huge issue. The components are getting hit with these repeated intense pressure waves. Finding materials that can survive that long term is critical. And then there's just the challenge of scaling up designs that work in the lab and integrating them into actual full-size vehicles. That involves manufacturing, controls, the whole system working together.
So it's not just plug and play. A lot of fundamental engineering still needs solving, but people are working on it. The reports mentioned ongoing research.
Oh, for sure. Major players like NASA, the U.S. Air Force, national labs, they're all heavily involved. They're using really powerful computer simulations to understand exactly what's happening inside these engines. Additive manufacturing 3D printing is also proving really useful for making the complex shapes needed and testing new materials quickly. And there's work using AI, artificial intelligence, for real-time monitoring and control, trying to keep that combustion stable and efficient.
Okay, so what does this all mean when you look at the bigger picture? The reports mentioned the sort of global competition in hypersonics.
Right. If you connect the tech development to geopolitics, RDRE progress is definitely linked to that global hypersonic race. The reports outline programs in the U.S., China, Russia. For the U.S., NASA, the Air Force Research Lab, contractors like Lockheed Martin are clearly working on RDREs. Information on China's specific RDRE efforts is, less public. Russia is also known to be doing research in this area. If the U.S. can really master RDREs, it could give them a significant edge, particularly in developing reusable hypersonic platforms and potentially impacting, space dominance, too.
So looking ahead then, what kind of timeline are we talking about? When might we actually see these things in use?
The report sketched out a possible timeline, maybe seeing test vehicles, missiles, drones with RDREs integrated sometime between, say, 2025 and 2027. After that, maybe initial deployment in actual military systems between 2027 and 2030. And then for the commercial side, those super fast planes or orbital platforms, the projection is more like the 2030 to 2040 timeframe.
So realistically, within the next, 10 to 15 years, we could see the start of a really profound shift in both military capabilities and maybe even how we fly commercially, all driven by this different way of generating thrust.
That's the potential, yes. It's not just a slightly better engine. RDREs could be a foundational shift, could drive growth in the space economy, enable ultra-fast global logistics, and yes, change the nature of future conflict.
It's definitely clear that these rotating detonation rocket engines are way more than just an incremental upgrade. They feel like a potential strategic key, unlocking a lot of future aerospace developments. So considering all the potential for incredibly fast global travel on one hand and a significant shift in defense tech on the other, what kind of unforeseen societal changes or maybe geopolitical ripples might widespread RDRE adoption actually lead to down the road? Something to think about.